So today we'll be continuing our Habitable Planet series with a discussion of rogue planets. If you've just jumped in this series by starting with this video, you might want to go back and see the first one on dwarf planets before watching this, as much of the material in that video relates to this one. Also, like all the links that will pop up in these videos with the yellow or white box around them, you can just click on it and it will pause this video and open that one in a new window. Similarly, if you're new to this channel, you should probably turn on the closed captions. Easier to understand with subtitles on. So let's begin with the obvious. What is a rogue planet? In a nutshell, rogue planets are objects that were either ejected from their native solar system or formed entirely in interstellar space. So technically, they are not planets at all. That's not new for this series though. We started by looking at dwarf planets like Pluto, and last time we looked at large moons. Only one of our videos in the series has actually revolved around a classic planet. And that will continue to be the norm for this series because, to put it simply, regular planets around regular suns is terribly boring. Now, it has been over a century and a half since Darwin published, and we still don't know how abiogenesis actually occurred. The leading scientific candidates are hydrothermal vents, tidal pools, and panspermia in basically that order. But we don't really know because we can't see the process in action, and unsurprisingly, it is rather tricky to hunt for evidence from billions of years ago. Truth be told, all three of those options might allow abiogenesis, or none of them might, and we need a new theory. But it does seem plausible that however it occurred here on Earth, it probably can occur on planets a lot like our own, around the stars that are a lot like our own. Similarly, if you've watched the terraforming video, you know that colonizing any planet is a major undertaking, but the more like Earth it is, the easier it is. So looking at how life might originate on Earth-like planets, or how we might colonize them, just isn't all that interesting. In this series, we're interested in the hard cases, the abnormalities. The places that don't seem like life could occur on them, or wouldn't seem like places we want to make our home. Rogue planets, at first glance, are practically the epitome of that. Icy cold worlds without a speck of sunlight, totally inhospitable to life. But on second glance, they may be a lot more hospitable than they initially look, both as a source of life and as a place we might want to colonize. Indeed, for the latter, for colonization, as we'll see in the upcoming interstellar colonization video, they may be the most valuable real estate around, and the keystone of us getting out among the stars. Another thing to keep in mind is that rogue planet is a very broad territory term. When we use it, we're not really talking about Earth-sized objects, which are a narrow and special, though interesting case we'll look at, sometimes called Steppenwolf planets. We really mean just about anything from a decent-sized asteroid up to a gas giant bigger than Jupiter that might have its own moon. Essentially, we mean any object out in the interstellar void, and that's a big category. Tons of things would fall within it, with nothing more in common with each other than being decently large and devoid of sunlight. Once you get away from a sun's light, the energy to power life has to come from something else, and life needs a power source. Now, back in the first video, when discussing Pluto, we pointed out a couple of these, as well as some alternative chemistries life might use besides how we do it on Earth. For power, we have tidal heating from a moon, and rogue planets can have moons. They could acquire some while wandering out in their solar system or picking one up in deep space, and they might have decent odds of keeping their original one too. Tidal heating can be a very powerful energy source, especially when not eclipsed by sunlight. Nuclear isotopes like uranium down the core world provide heating as an option as well. Gravitational contraction generating heat is also an option for larger objects like gas giants. None of these provide much power though, and that matters because even though you could have a warm planet far from the sun, it doesn't necessarily mean there's power for life. Life can't thrive just because a place is warm. It needs incoming energy, energy flux. There's life that lives in subterranean caverns here on Earth, for instance, but it's very diffuse, way less biomass than the surface has, usually slow metabolism creatures and plants too. Unexposed to the sun, such life has lived mostly off the waste of solar-powered ecosystems above, or the trickles of energy available from things like thermal vents or chemicals which it can metabolize for energy. Photosynthesis is the way we get really dense life, and that's mostly off the table for rogue planets. I say mostly, not entirely, because objects do give off photons at a rate and wavelength connected to their temperature, and we found not only organisms that live off the heat and chemicals coming out of our hydrothermal vents, but also some organisms, like some types of green sulfur bacteria, that can live off their light too. Infrared light, especially mid-IR range light, often known as thermal light, is not going to give you super abundant growth either, but it does add one more power source to our pool. Energy available for life does need to be a steady source, and the more, the better. But even on a decent-sized asteroid, you could have chunks of uranium in the core decaying and giving off heat that emerge from cracks in the pockets of mineral-rich water. And that's basically the same condition that you have for Earth's own ocean smokers that are the lead candidate for abiogenesis of life on Earth. Ditto, as I mentioned, there wouldn't be anything strange about two rogues being in orbit of each other and giving us tidal heating, as we discussed on the video on tidal locking. You could also have pockets of radioactive material right inside or near our underground pockets of mineral-rich water, acting as a natural nuclear fission reactor. We've seen this even on Earth. Groundwater seeps into places with dense uranium deposits and acts as a neutron moderator, just as in our own fission plants, increasing power output of these deposits beyond natural decay. Now the next step to keep in mind, looking at rogue planets, is they probably wouldn't be large rocks in the void. Earth has very little hydrogen and helium, and even other gases are pretty thin and rare, because the sun strips atmospheres off planets, as we discussed in the terraforming video. There is ionizing radiation in deep space, but not that much of it, and no regular light to warm the planet's surface to make the atmosphere stripping process easier. So any object in the void is likely to acquire a lot of interstellar gas. If you've got miles deep layers of hydrogen and helium surrounding your world, that makes for one heck of an insulating blanket, and strongly implies the possibility of oceans on these rogue planets. Just taking the example of a rogue gas giant with moons, like Titan Europa, place we already consider possible candidates for life, very little of their mechanics rely on the sun. Titan has a thick nitrogen atmosphere, also strong in methane, that's warmed largely by rotating around Saturn. Europa is a large ocean crusted over with ice that's also tightly heated by Jupiter. If life could evolve on either one of those, then it could evolve on parallel worlds in interstellar voids just as easily. What about Earth-like planets? In fact, let's consider what would happen if the Earth and its moon were ejected from our solar system. Needless to say, such an ejection, combined with a loss of light, would kill nearly all, if not all, life on Earth. Though it would take a long time for some of it to die, and some might not die at all. There's a lot of heat on Earth, and the cooler you get, the slower you radiate heat away. What's more, as planets cool, the oceans freeze over and begin making an insulating blanket that traps heat in the deep ocean. By that point, all the water is frozen on the surface, but the air is still around. Nitrogen and oxygen don't liquefy till you get a good bit colder. But under the ice sheet, all the heat trapped, which is still being produced by radioactive materials in the core, are keeping the deep oceans warm, leaking out through wormhole hydrothermal vents where life will continue. We'd also still be getting tidal heating off our own moon to further warm things and store the pot. Now eventually that atmosphere will liquefy too. The heat produced by our planet's core is only about a 3,000th of what we get from the sun, and keeping in mind that fourth power rule of heat radiation, we'd expect the temp to drop to about the fourth power of 3,000 less than now, which is about 7 or 8 times cooler, somewhere around 40 Kelvin, which is cold enough for nitrogen and oxygen and argon to liquefy, but not quite cold enough for hydrogen to liquefy. Pretty close, but not quite. And helium takes even lower temperatures. So as Earth drifted out into the void, we'd start collecting hydrogen and helium gases in the new atmosphere. Very slowly, but it would begin to accumulate, and we'd also nab us some comets and other stuff. If we get enough, it might even create high enough pressures and temperatures under that new atmosphere to turn nitrogen and oxygen back into air. So you've got a water ocean under the ice, and possibly a second ocean of liquid oxygen and nitrogen on top of that, and an increasingly thick hydrogen and helium atmosphere over that. Planets significantly bigger than Earth will be even warmer, while smaller ones will be colder, but we'd expect just about any object large enough to get dubbed a planet to act this way. These sorts of worlds are sometimes known as Steppenwolf planets, or Steppenworlds, for the comparison to a lone wolf of the steppes, and would specifically be any planets with a mass from a little less than a third of Earth's to a little over triple Earth's mass. These planets would have an insulating layer of ice and carbon dioxide snow, and whatever else they picked up touring the lonely void to allow subsurface liquid oceans heated by geothermal activity coming up from those hydrothermal vents. Now we can't be too sure of the existence of Steppenwolf planets, which are rogue planets with subsurface oceans, because we can't really predict too well how thick that ice would end up being on a given planet. Ice will grow from the surface down until it reaches equilibrium with the heat coming from the mantle, but that is going to vary a lot from world to world, and our best guess is for Earth it would be nearly a kilometer deep. For smaller worlds, it could be several miles, and dynamic gets further messed up depending on whether most of the heat is transported by convection or conduction. These Steppenwolf planets are our main interest today because life on smaller planets, essentially icy dwarfs or asteroids, is another subject we've already partially addressed, or wouldn't be much different in the case of an asteroid from being in our own belt or in deep space. Ditto gas giants themselves, rather than their moons, will be looked at later in the series, because rogue planets, or just in deep orbit around their own sun, they act mostly the same. There's pretty good odds Steppenwolf planets decently larger than Earth would have deeper oceans, and would actually get more radioactive heating. After all, a planet of similar makeup and density to Earth, but, say, twice as massive, would have twice the radioactive heating and twice the water, but only 60% more surface area for that water to be on and for that heat to escape from. Super-Earth Steppenwolf planets might be able to support fairly robust underwater ecosystems, albeit rather anemic compared to our own ocean life. Even the deep sea life, which on Earth gains a second power source from organic matter sinking down from the higher levels that are fed by sunlight. And there might be a lot of these worlds. Some estimates right now place that number of rogue planets, objects ranging from as small as bigger moons like Europa and Titan, up to super Jupiters, may number around 100,000 per every star, meaning there'd be a lot more of them than objects of similar size in our own solar system, which is only in the area of around 100, not 100,000. This doesn't even include smaller objects like asteroids, which we might expect to be even more common. But if for the moment we assume this estimate was right, and those were fairly evenly distributed in space, these objects would only be spaced a few light weeks apart. That's a long cry from the light hours of spacing of our own mid to outer solar system, but a lot closer than the few light years between other solar systems. Now, if you start tossing in asteroids, well, there are around 1 million asteroids a mile across or bigger just in our asteroid belt, more than 1,000 times as common as the various planets and larger moons we have. And if that ratio held up, you'd expect interstellar space, where planets might be common enough to appear every few light weeks, to be as common as every light day or two. We'll talk more about making rocks like that livable in the future, though if you saw the video on fusion, you can take a guess as to how. But this will be an important point when we get to interstellar colonization, because it means the solar systems are not these lonely islands in space years away from the nearest neighbor, but really more like cities dotting a vast perpetual plain of rural land. Now, getting back to Steppenwolf planets, the ones of a mass and an internal composition fairly close to Earth's, we've seen that they aren't too bad of places for life to maybe emerge on, but like we discussed in the case of Pluto, not places you'd expect life to be abundant on if it exists at all. How could we change that? How would we colonize a place like that? Well, again, if you've seen the fusion video, you know how we'd have the option to just manually light the place. I mentioned in that video that to light a square mile of land artificially, like the Earth train normally gets, would require about 10 to the 16th joules of energy a year, or about 10 kilograms of fusion fuel, hydrogen or deuterium, both of which are quite common in deep space. To light an entire planet the size of Earth as well as our sun does, to fake a sun, would require a lot more juice, something like 5 or 6 megatons of fusion fuel a year, which sounds like a lot, but for comparison, if that planet had a hydrogen atmosphere of the same mass as Earth's, which is about 5 billion megatons of air, then you have a billion-year supply just from that. Not to mention all the hydrogen in the oceans. Our own ocean is roughly 1,000 times more massive than our atmosphere. So if we stuck a fake sun in orbit around the world, say, orbiting every 24 hours and shining a beam down like a flashlight, sort of like the geocentric model where the sun orbits the planet, you could run that as long as a normal star lived, and a normal planet lived, without putting a very big dent in your local fuel supply. Of course, if you're colonizing a Steppenwolf planet, you might not want to go that route. You might instead decide to keep it frozen and just stick some submersible fusion plants in the ocean, trailing strings of light and introducing photosynthetic organisms to it. You could even do something like this on Earth. If you want the great ocean depths to have more life in them, you could just stick a floating fusion power plant somewhere and flush all the cooling water down along pipes with photosynthetic optimized LED lights running down far beneath the sun's reach. Especially if you add in some meshes to collect minerals and tridus, you could end up with long, gorgeous vertical coral reefs harboring huge amounts of marine life. Even if the planet already had life, down near the bottom where the hydrothermal vents were, you could attach cities to the ice up top and slowly melt it till it was just a fairly thin layer of ice, maybe a few hundred meters thick. Then in those new upper regions, you could attach strings which provide light and aerate the water, and introduce earth marine life, the detritus of which could sink to the depths and help fuel the native ecology. Done properly, the two could be kept separate and safe, while allowing two ecosystems to thrive, with the original one now much more robust. I'm not sure how practical that is compared to other colonization routes, but personally I find the idea of a Leviathan depths with trailing lights providing an oasis of life pretty neat. So that's going to wrap it up for rogue planets for now. We'll look at how the smaller and likely more common rogue asteroids might be made habitable in the upcoming video on rotating habitats in our megastructure series. Then talk about the importance of rogue planets to interstellar expansion and civilization in the upcoming video on interstellar colonization. If you want a reminder when those videos come out, click the subscribe button. As always, questions and comments are welcome. And if you enjoyed the video, hit the like button and share it with others. Thanks for watching, and have a great day.
In previous videos on the Fermi paradox, we discussed a number of solutions to the question of why life seems so rare in the universe. One of the more popular scenarios is called the rare earth option. But rather than just doing a video discussing that in more detail than we already have, we'll use it as a segue into a separate series. We're going to look at all the weird planets, and even non-planets, where life might just conceivably get a foothold. And while we'll still be raising all the problems and hurdles life would have existing in these places, we will be looking at it from a more optimistic viewpoint. To commemorate the flyby of Pluto taking place at the time I'm recording this, we are going to start off by looking at how life might be able to live on a place like Pluto, a relatively small planet far from a star's warming light. So we will be looking at Pluto and worlds like Pluto in this first installment. We will look at how they might conceivably host life, and also how such worlds might be colonized to be homes to humans or other technological species. In future installments, we'll be looking at everything from worlds around red dwarf stars or on moons around gas giants, or even in gas giants, both those near stars or rogue worlds out in the interstellar void. We'll look at how life might live in a comet or an asteroid. We'll try to cover all the reasonable options, and even some of the crazier ones. Hit the subscribe button if you want to be alerted when those new episodes come out. So if you've seen previous videos, you'll probably notice I've started adding in some animations. We've got two other new features as well. First, we'll be trying to keep these videos shorter.
Yay!
And second, I'll be experimenting with adding in subtitles.
Yay!
I know I'm a bit hard to follow sometimes, and remind people of some fictional characters. If you're curious, it is a speech impediment, not an accent. Hopefully with the subtitles, it'll be easier for some of you to follow. Assuming it works, of course. So let's get started. I want to emphasize that this is a very hypothetical video. Personally, I doubt we'd find life on Pluto, even very simple organisms. But we can't rule it out completely. It isn't just that such life might run on weird chemistry compared to our own. There could be habitable pockets where Earth-like life could live. What about that really alien life, though? Pluto and worlds like it are basically oversized comets. Most of the material is stuff that would melt or evaporate if it were on Earth. Ice, ammonia, methane, carbon dioxide, and even oxygen and nitrogen are frozen solid there. But hydrogen and helium are not. Hydrogen doesn't freeze till it gets even colder than Pluto gets, so worlds like it, even ones in the interstellar void, could easily have liquid hydrogen in abundance. When we're talking about life, the key thing is a power source. Hydrogen burns, so you could conceivably have an organism on the supercold worlds that drank liquid hydrogen and frozen oxygen and used that as a fuel or food. Pretty out there, but probably not impossible. But what about Earth-like life? Is that at all possible? Throughout this series, we'll mention over and over that the key thing life needs is a fuel. It needs a power source. But to be at all Earth-like, it needs pressure and temperature too. If you're far from a sun, your options are limited. But we've got two big ones. First, a lot of worlds have pockets of radioactive materials. Those decay with time, but are also a lot more plentiful for that reason when a world is younger. Uranium, potassium, and other substances will give off some warmth just as they do for Earth. When planets form, matter falls down on them and impacts, so they tend to be very hot from absorbing all that, and they may have a steady flow of meteor impacts adding some heat over with time. Between radioactive materials and impacts, a planet may be warm and retain warm pockets deep beneath its surface. There's also tidal heating. If a planet has a moon, and Pluto does, actually it has several, then the constant distortions of gravity yanking on the world can keep it quite warm. This is what keeps Jupiter's moon Io a ball of molten lava. So while surface life, walking around and breathing air probably isn't in the cards with anything like normal Earth life, there could be deep and massive oceans on these planets. Indeed, we're pretty sure Pluto does have underground oceans, and that even its largest moon, Charon, might have some. Where you've got liquid water being churned out, with minerals dissolved in it, you have the possibility for life. We still don't know what started life here on Earth, or if our main candidates of underwater thermal vents, so-called black smokers, are the only way for it to merge, if that's what started things off here in the first place. But regardless of how it gets started, once in place, life could be able to thrive in any ocean so long as there's some power source storing up the water. Throughout this series, we'll see that there's a lot of candidates for that which wouldn't even qualify as a dwarf planet like Pluto, let alone an Earth-sized planet. Now, complex life, especially intelligent tool users, is a different story. Ocean life obviously can't support fire or many of the other technological precursors like metallurgy, pottery, glass blowing, or even basic chemistry. It's kind of hard to mix solutions in water. There's also the matter of thriving being somewhat relative. We have a long and dense food chain because everything runs on abundant sunlight. If you're familiar with life down in caves or the deep oceans, you know that those are all optimized to run on very little energy, and they still get most of that from debris flowing down from where there is sunlight. Some life-bearing Pluto equivalent could easily have less than 1% of our biomass, and still all spread out. And it's rather hard to develop a civilization when you are spread out. Our hunter-gatherers need around a square mile per person to live, far more in tundra or desert climates, and that limited them a lot on developing. If you're 100 or 1,000 times more spread out to gather food, you'd have some serious roadblocks to forming civilizations. So we can't rule it out, but where simple life, and even animal life, are reasonable expectations off worlds like Pluto, that expectation would have to be far smaller where anything really complex like us is concerned. The next thing to consider is what do we mean by worlds like Pluto? Pluto's small, smaller than our own moon even. It's cold. It has a large moon that isn't just tidally locked to it, but to which is tidally locked to as well. Which of these factors apply to what we've been talking about here? Well, a bigger planet, say Earth, transported out there and left for, 1 billion years to orbit around it, would behave a lot differently. It will have a thicker atmosphere. Pluto has one, but barely worth mentioning, just like the Moon has one. Earth's atmosphere contains virtually no hydrogen except where it's locked up in molecules like water or methane, because molecular hydrogen doesn't stick around on warm planets. But it's the most common substance in the universe, so an Earth-mass planet could easily have an ocean and atmospheres made of molecular hydrogen. It would probably be warmer too, since heat loss in a vacuum is all about surface area. More surface, more heat loss. Pluto might only have about 0.2% of Earth's mass, but it has nearly 3% of its surface area, a 15-to-1 higher ratio. So when it comes to heat derived from radioactive decays, bigger planets will stay warmer. If we're pondering a low-temperature life form that uses liquid or gaseous hydrogen instead of air or water the way we do, you could have life swimming around in surface oceans of Earth-mass worlds that weren't even near a star. As to Pluto-like world in mass and composition near a star, it would probably evaporate. Pluto is more like a giant comet than a planet or an asteroid. Another reason it has a relatively large surface area, it just isn't very dense. But a less massive world than Earth, even one less massive than Mars, could actually retain a thick atmosphere. There is a misconception from the Moon and Mars that gravity is a key there, which it mostly is, but there's a lot more leeway on it than people tend to think. We'll discuss that in future videos on life for more or less massive planets. Last thing, what about colonizing a place like Pluto? Can we, with the kind of technology we have now, or can reasonably predict we'll get, live on a place like Pluto? The answer is basically a straight yes. Even without some power source like fusion or old-school nuclear fission, we can power ourselves out there. Burning hydrogen and oxygen, or methane and oxygen, specifically on Pluto, isn't very viable because there's not a lot of oxygen around there except as water, but there is some, and other Pluto-like worlds might have more. Plus, not everything needs oxygen to burn. For instance, the spacecraft flying by Pluto right now has hydrazine thrusters, and that's a mix of nitrogen and hydrogen, both abundant on Pluto, and it doesn't need oxygen to create thrust and heat. So chemical power isn't totally ruled out, even for Pluto, let alone other parallel worlds. Nor is solar power. The sunlight out there is barely 1,000th of what it is here in intensity, but 1 watt per square meter is still nothing to shrug at. That's actually brighter than the night under a full moon. A 10-watt LED light in a room in your house is delivering light comparable to what you get from the sun out there, so it isn't dark. What's more, you've got options like solar mirrors. The idea of creating planet-sized mirrors to reflect more sunlight onto a world sounds very crazy, but when you're talking about mirrors that only need to be as thick as paper, or even thinner, manufacturing ones the size of whole planets can be done with less mass than you'd have even a very small moon no bigger than a modest mountain on Earth. If you've seen my original YouTube video, Megastructures, then you know doing something like that is actually very modest compared to some of the projects we envision getting ourselves up to in the future. So, even if we never figure out fusion, these freezing cold worlds aren't necessarily off our radar to put habitations on. Though obviously that would be ideal, followed by good old fission power with something like uranium or thorium. Gravity isn't necessarily an issue either. It's very low on Pluto, about 7% of Earth normal, compared to 16% on the Moon. But as also mentioned in that Megastructures video, centrifugal or spin gravity isn't limited just to use in zero or microgravity environment. Instead of using a spinning cylinder, you just slope the floors to combine natural gravity with spin, just like how water in your washing machine will form a sloped surface when spinning as gravity and centrifugal forces add their power together. You can do that on a low-gravity world to create an effective, decent gravity. You don't need to build sturdy surface domes either. You dig in a few hundred feet deep on Pluto, and the pressure of the ice over you will keep pockets of air at normal Earth pressures. This would also protect you from cosmic rays and micrometeors in the absence of an atmosphere or magnetosphere. You'd have to artificially light and heat the place so you could grow food, but we can do pretty dense and efficient hydroponics when we need to. So, in summary, can we colonize a place like Pluto? Yeah. Can life evolve there naturally? Quite possibly, though not likely anything we could chat with. I hope you've enjoyed this first video on planetary habitability. Don't forget to hit the like button if you have, and subscribe if you want to be alerted to future ones. Feel free to leave a comment below. I read them all and I try to reply to questions. And check out my other vids. Have a great day and thanks for watching.